Alright. Today we're going to learn about state functions and enthalpy. So here we go. Now, the state function is simply just a property of a system that is determined by the specifying of its condition or state, which means what is it at that current moment. So like temperature, pressure, location, etc. All those are considered to be state functions. Now, a state function, the big difference between it and anything else is that it only depends on its present condition, not how it got there. So in the case of temperature, we don't really care why the temperature went up, just the fact that the temperature went up is what's important. That's what makes it a state function. So if we look at some examples, if you went from Chicago to Denver, the change in altitude is always considered to be a state function because no matter what, the change in altitude is roughly 4,684 feet, regardless of how you did it. It doesn't matter, the distance that you travel may not be a state function because that depends on your path. If you fly here from Chicago to Denver, you're still going to change a net change of altitude of 4,684 feet, but that's significantly less travel time or distance than if you were to say drive there, because now you got to drive and take a big winding path to get there. So the traveling part, the distance you travel, is not a state function because that does depend on how you get there, whereas the actual end result of just going from Chicago to Denver, that is a state function. Internal energy, which is something we've learned about and talked about a lot, is a state function because it only depends on the initial and final states of the system, not how that change occurs. We only care about ending and beginning of the energy, not what did it to it. Work, however, is not a state function because if you think about it, depending on what you do to do that work, it's going to change. Now, enthalpy is the amount of heat absorbed or released under constant pressure. So basically, it's your change in heat. The symbol for it is a capital H, so it's the heat content. The weird thing about that is you can't actually measure the heat content of something. So what we do focus on is how that enthalpy changes. So we look at more like the delta H, because we can get if a temperature goes up or go down. We can't really just measure like, boom, this is how much heat energy is actually in there. Now the formula for it should look really familiar because it's simply just final heat minus initial heat, which looks exactly like the energy one we talked about the other day. So positive delta H is going to be endothermic and a negative delta H is going to be exothermic. So the question is, enthalpy, is it going to be a state function or is it not going to be a state function? The answer, of course, is that's right. You guys are so smart. Cool. So it's a state function because we don't really care how the heat changes. We just care that it actually does. Now, we talked about this before, so just to recap, endothermic, exothermic. Endothermic is heat flowing into a system from the surroundings. Exothermic is heat flowing out of the system from surroundings. That's going to become very apparent and important as we kind of work through everything else. So one of the things we're most concerned with is the enthalpies of reaction, or the delta H of the reaction. It's also sometimes known as the heat of the reaction, because now we want to know after a reaction has taken place, has it gained heat or has it lost heat? They're hugely important. Reactions and enthalpy are tied to each other, because most often the way that heat is transferred in a reaction is through heat. So an example, if we took the one hydrogen reacting with oxygen, roughly 483.6 kilojoules of energy is released. So that's heat being released, so delta H is negative. Therefore, it's an exothermic reaction. Conversely to that, SO2 plus 2H2O, you're going to add in 129.6 kilojoules of energy, and you're going to produce hydrogen gas and sulfuric acid. So in that case, you have a positive delta H. And what happens is heat's being absorbed by the system, all the surroundings around it, so the system absorbs all of that and makes it an endothermic reaction. The fact that we have these two energies added in, both product and reactant, makes it a thermochemical equation. Adding in that energy identifies it and tells you how much energy you're using throughout the reaction. So another important thing about enthalpy is the fact that the amount of stuff that you use makes a huge difference in terms of how much enthalpy there is. The more of a substance you got, the more heat you can release, which hopefully just kind of logically makes sense. If we look here with 1 mole of methane, we get negative 802 kilojoules for our delta H. So 802 kilojoules would be released. If you put 2 moles, what do you think is going to happen? Yeah, that's right. It's going to be doubled. So you get 2 times as much. The cool thing with enthalpy is it can be used as a conversion factor. Now, I know you guys all love stoichiometry. I know it because I see it in your faces every single day when I say we're going to do conversion factors. You'll love it. So here we go. Methane plus oxygen gives you carbon dioxide and water. Simple reaction, combustion reaction, has a delta H of negative 802 kilojoules. Now, that is if you have exactly 1 mole of methane. If you don't have 1 mole of methane, though, you got to do a little math. Not anything crazy. So what happens if you only have 4.5 grams of this methane that you're burning? Well, here's where we got to do a little stoichiometry. So you're going to take your 4.50 grams of methane, and as you know, we typically have to turn that into moles. And the way you do that is using the molar mass. So the molar mass of methane is 16.05 grams. Now the thing is, we don't want moles, we want no energy. The cool thing is, we just said a second ago that 802 kilojoules is released when you burn 1 mole of methane. That can be written this way, with negative 802 kilojoules on top, 1 mole on the bottom, because now we're using that as a conversion to allow us to go from methane into energy. The negative sign is important though. You can't leave that off, because that negative is what's going to allow you to understand whether or not you're gaining or losing that energy. The answer comes out to be negative 225 kilojoules with correct significant figures. The negative is important because now we know that we're releasing 225 kilojoules instead of 802 kilojoules. So 4.5 grams, definitely not a mole. A lot less energy is released. So hopefully that just kind of makes sense. That's a way to quick check. So just to recap, that negative 802 kilojoules per mole of methane is your conversion factor, and you get that from your balanced chemical equation. Now you can flip that on itself. If you're given energy and you're finding moles, you just turn it over, just like we did with molarity and anything else. A couple more things real quick. If you reverse the direction of the reaction, you have to flip the arrow around, right? So now our reactants become our products and our products become our reactants. The value of the delta H, the magnitude, is going to stay exactly the same. The only thing that's going to change is the sign. So methane reacting with oxygen to produce carbon dioxide and water gives you negative 802 kilojoules. If you were somehow able to get that reaction to go the other way, where you took carbon dioxide and water and combined them to form methane and oxygen, now you would have to absorb 802 kilojoules. You'd have to push 802 kilojoules of energy into that reaction to get it to form. Probably not a very viable thing to do, but for example, it shows you how all that's happening is we're keeping the numerical value the same. We're just flipping those arrows around to indicate that it went from being exothermic when we went from methane to CO2 and water, and when we go the other way around, we flip that arrow around. Now we have to have the sign the other way to show that it's an endothermic reaction. So one more thing you're probably going to be wondering about is, well, what about the state? Because we always do state symbols, gas, liquid, aqueous, and all this kind of stuff. Does that make a difference? Well, the answer is yes. It makes a huge difference. The state of the reactants and the products affects the change in enthalpy. Due to state changes requiring energy being gained or lost, you're going to have a different amount. So for example, we've got methane plus oxygen gas, all gases, producing gaseous CO2 and water vapor. You get 802 kilojoules produced. But if you somehow do conditions where you have the same reaction take place, but you get liquid water that forms instead, you actually end up with a change of negative 890 kilojoules of energy. So more energy is released if you get it to be liquid water instead of gaseous water. Now, if you just think about what's happening in terms of going from a gas to a liquid, it'll hopefully make sense. Because to go from liquid to gas, you got to heat it up, right? The temperature change, got to get to 100 degrees Celsius, put more heat into it. That increases the molecular movement. Water vapor, gas evaporates off. So what happens is just the state change from water, that's a liquid, to gas state requires 88 kilojoules of energy. So if you think back to the other reaction, by just keeping it as a liquid, more of that energy can be released to the surroundings. If some of that energy is, if it's going to be a gas, some of that energy, or 88 kilojoules, has to be used to turn it into a gas. So hopefully this kind of makes sense. We'll talk more in class. See you later. Whoa!